So here we're going to create a new C++ class. We'll include a string. And so we're going to say that a brother has a std : string for their name. This is what we're talking about, the protection. Private means nobody else can access this member variable. And public means anybody can. So we'll provide a constructor for our brother that takes in a std const std : string reference name. And a brother is also going to have one other thing. So let me new C++ class sister. Include string, and then yeah, we can, but normally they'd be split up separately like they are here. You'd have one .h file and one .cpp file per class. And then we're also going to include brother.h. And so we're going to have a brother pointer called bro. And then over here in brother.h, we are going to have a sister. And our brother is going to have a sister pointer sis. And so here we're also going to accept as an argument a sister pointer sister. And so this is our creation of the constructor. So we said a brother to create your brother, you need to pass in a their name, and you need to pass in a pointer to their sister. And in sister.h, we will provide the same thing. So public. So basically, public means anybody outside your class can access it, as well as yourself. Private means only inside the class can you access it. So we'll have a sister, and it's going to take in a const std string reference name, and then a brother pointer. And so if we go back over here to brother.h, we're going to say generate definition for constructor brother. And this is going to be our initializer list. This is where things look weird. Name, sis, sister. You're like, well, what does that mean? Right? So notice, I don't know if you can see that the color of these two guys are a light purple. I'm not sure if that's actually visible, but they are. And the thing here is that we're saying our member named name is going to be initialized to the value of this argument name. Our member named sis is going to be initialized from the member named sister. Does that make sense? And we're going to do the same thing in sister.h, but we can be like a lot smarter, and we can say code generate. I want you to generate a constructor for me with these two parameters. Okay. Yeah. Hi, thank you. Right, and so it made that value, and I've double defined it, so I'll get rid of one of these. Right, so you can have the compiler generate some things for you. We can also say code, I would like you to generate a getter for me, and I want you to get a getter for my name. And so it made some code here, and this says, hey, inside the sister class, there's a function called getName. Const means it doesn't modify the sister, and it's going to return back the name. Right? And then we will also do code generate getter and setter for their sibling. So it just does an assignment. And we're going to go back and brother and more or less do the same thing. So code generate getter for your name and code generate getter and setter for your sister. Everyone following along so far? Are there any questions? Yeah. So in a lot of ways, classes create their own namespace, and the namespace is the name of the class. So this is like saying inside the brother class. Inside the brother class, there's a function called getName, or inside the brother namespace. So classes also create their own namespaces too. So is it weird that I have to say brother : getName here? So if your function is defined outside of the class, yes, you have to do this. Otherwise, we would just be creating a function called getName that wasn't a member of brother. So if I had defined the function inside here, like if I had put like get sister over here, and I just said, return get sis, or return like sis here, this would be fine. And I wouldn't need to say sister pointer sister : get sis, because I'm inside. I wouldn't need to say sister pointer brother : get sis inside the brother class, because I'm already here. But now, since I'm outside the class, at this point over here in brother.cpp, notice I'm not inside like namespace brother. I have to say, hey, brother : get name. And I've never tried just doing brother curly brackets to see if that works before with classes, because this is the way I was taught to do the out of class definitions of the functions. So this is like out of class declaration means it's not inside the class definition over here. Yeah, it's outside the class, right? Because it's not inside class brother, right? But to specify that this function really is a part of the brother class, it really should be inside brother, I say brother : Yeah, there's a dot .cpp and a .h. The .h has the declaration of the class. What's the class file? It's not. This is not Java. Java has .class files, but yes. So the declaration of the class is inside the .h file, and the definitions of the functions are inside the .cpp. Anything else? Yeah. Where are they defined? You mean like, how did I do that inside CLine, or? Yeah, it's right here. Because you want to get the brother sister, right? And inside the sister, you want to be able to get the sister's brother. Does it make sense? So over here in main, right, we might do something like I want, to include brother and sister. And then so I might want a brother, I don't know, John, and John's name should be John. And for right now, since John doesn't have the sister class hasn't been initialized yet, we're going to pass a null pointer. Right? He's not currently pointing to a sister. He doesn't have one. Then we have a sister, right? I don't know, Alex. Her name is Alex. And then Alex might have as her brother, John. And again, they're not asserting any ownership over each other. They're not create a constructor for that. Take a string name and a brother pointer. the string. Oh, we'll figure out what that is. And then we might do something like John dot set sister to be the address of Alex. Like, I'm just kind of like, just trying to see if I'm going crazy here. Okay. I think it's a different problem, but we'll get to it in a second, right? So we're going to set John's sister to be Alex. Then we might say out like cout std : cout. No, that's not. John dot get name sister is John dot get sis arrow get name. And then we could repeat and then get sis, thanks. And new line. And then we might say Alex dot get names brother is Alex dot get bro get name. Cool. Any questions so far? Program ends after that. And notice I'm using dumb pointers because I'm not trying to assert ownership over that person that I'm pointing to. Yeah. I set her brother up here at the beginning. Right, I said, hey, your brother is John. So any questions here? Yeah. Why did I set it to null pointer here? Yeah. I set it to null pointer here because it would pass a value in. Right, something has to go there. And since I haven't created an instance of a sister yet, I'm temporarily putting it as null pointer to then set it on line 8. Anything else? So we have sad days in our lives because this won't compile. And you get this long blah about why things are bad. And it's saying, hey, brother has not been declared. And it's saying, like, over here in sister.h on line 13, I don't know what a brother is. But didn't I include brother.h? Right, and some of the things are from, so brother.cpp tried to include brother.h, and then brother.h included sister.h, right? And then we ran into problems. So this is the circular inclusion problem, and I don't remember if we talked about that in this class today. And the reason has to do with how C processes files, right? It goes top down, one pass through them. So let's see what happens when we try to play the role as the compiler. And I want a new scratch file. That's not what it's called. So over here, right, we're in brother.cpp, right? And so we attempt to include brother.h. So what does pound include mean? Copy paste, right? So we go to brother.h and we attempt to copy and paste all this stuff in here. So we'll copy and paste this in here. But when we're doing the copying and pasting of brother, what do we need to include? Sister. So we'll go over here into sister.h. And so we'll copy and paste everything here inside sister. We'll replace this pound include of sister with the value copy and pasted in. And that's really what happens. And so one of the reasons that we don't have like this infinite loop of like sister trying to include brother again is because we have these guards. The first time we come into the file, brother.h hasn't been defined, so we define it, right? Then we include string. Then we go to check to see if sister underscore h hasn't been defined. It hasn't. We then go to include brother again, but oh, has brother underscore h been defined? You find it right here. It has, so we don't get in this infinite loop of one file trying to copy and paste itself an infinite number of times. That's really the key points of the guard. But now if we look down here, right, we can kind of like get rid of this line because it copy and pasted in nothing. So now if we look down here, we're like, okay, I have a new class sister, public, well, string, get name. A sister has a brother pointer. What's a brother pointer? Have you seen a symbol called brother at all yet? No. I don't know what a brother is. And this is the circular inclusion problem, because even if we had pasted things the other way around, with brother above sister, well then brother would be like, well, what's a sister? And the compiler would again complain. This is the circular inclusion problem, right? Because both of them are dependent on the types defined inside the other one. And so your question might be, well, how do we resolve this? In order to resolve this, you have to do what's called a forward declaration and just say that that class or that struct exists. So over here in brother.h, I would say class sister. Hey, there's a class called sister. And in sister.h, hey, there's a class called brother. Great. And now if we build, hey, we compiled. Right, but this can be like a really, really tricky, hard to find issue. Be like, why is this symbol not defined? I included you. It's defined right here. And it's because they have this circular relationship to each other. And so to fix that, you just have to say the thing exists. And then we're all fine and dandy because it knows that it exists. With a forward declaration, all that you can do with a forward declaration is you can have a reference to it, a pointer to it. You can accept it as an argument. You can return it as a type, I think, but you can't have an instance of it. So if all you say is like class brother, you can't actually say I want a brother called Bob, because that's all you know about. You'd still need to include brother.h to know how big is a brother and see what it's made up of and what its members are. Do you guys have any questions here? What? Oh, the other Alex error is now fine because we don't have the circular inclusions anymore. And you can see that we can even run now, and we should be happy. And we should be able to see something like John's sister is Alex. Alex's brother is John, right? Nothing too crazy. The craziness is the circular inclusion. And you can see that circular inclusion actually happening when you do the pound include copying and pasting into the areas. You see like, oh, I guess you don't know what that symbol actually is. But now at the top of each one of these, right, there's now like a class sister here. And then over here, there's a class brother. So now when we're going through, we can see, oh, hey, you've told me there's a symbol called brother. I'm okay with that for now. And then eventually once we get down here, oh, there's a class called sister. I already know about it, which is fine. But it also resolves the inclusion here as well, and we're also cool. Because if I got through the inclusion of sister, and it's all cool as well. So watch out for this. It's going to probably show up a bit in future homework assignments because a lot of times you need this self-reference, or not self-reference, but circular reference, right? For example, you might be making a game, and the game has like a pieces placed on the board for a particular player. So a player has pieces, right? But you might, want to go look at a particular piece and ask, who is that piece's player, right? And all you have reference to is the piece. So the piece has to keep track of who its player is, but the player has to also keep track of its pieces. And now we both need to know about each other, and we have a cycle. Sometimes these cycles aren't just like one level where it goes back and forth. Sometimes it might be like file 1 includes file 2, file 2 includes file 3, file 3 includes file 1. And so the cycle can be like longer than that, but you still end up with the same problem overall. Cool here? Okay, so you can refer back to that if you have questions. And then open this back up, and we'll talk a little bit more about CMake. Nope, we don't need smart pointers anymore. So you guys have worked a little bit with CMake, probably indirectly through CLion. So we're going to give a little bit more details about it, but I'll also let you know that I am a novice when it comes to CMake. I barely use it past its basic features, and so I don't know how everything works. One of the sad things also is that the CMake documentation can be really hard to understand if you've ever tried looking at it. And a lot of the tutorials are either like out of date or not good. So it's hard to find decent information about it online. So caveats there. But it is apparently a leading industry standard for doing cross compilation across multiple systems and for compiling C and C++ code, or at least putting the tools together to actually make the compilation happen. So the C in CMake doesn't actually stand for the language C. It stands for cross-platform. So it's a tool it's a build system to help you structure your code so it can be built across multiple different platforms. The reason that we need this is because different platforms have different specifications for compiling the same program, or where things might be located at, or different file name extensions, or different paths or areas you should be looking for finding libraries by default. And that's really annoying to deal with if you have to write it out by hand. So CMake tries to abstract that all away so that you're able just to focus on what needs to be done, and then it'll take care of the nitty-gritty details for you behind the scenes. Its work is split across two major steps. There's the configure step and the generate step. Configure is where CMake builds up its internal representation of the file, internal representation of the project, and also does other things like locating libraries, defining dependencies, setting different properties on different targets. And then it will generate. It'll create system-made build files needed to compile the project. So for example, on Unix, it might create make files. On Windows, it might create Visual Basic Solution files. On Mac, you can have it generate whatever the Xcode files are called that it uses. So you can have this one CMake file, and you can use it across multiple different platforms and still have it be able to build correctly in all of them. The instructions for configuration and generation are stored in that file called CMakeLists.txt. So this is a simple CMakeLists.txt file you've probably seen if you've opened it up inside CLion. So CMake minimum required version, your project, set, and then add executable. So the CMake minimum required, you say version and then whatever the version is. This is the lowest version of CMake that you need in order for your code to work. It is also going to set like the standards for that version so that even if CMake gets upgrades and changes the behavior of how certain commands or functions work, you'll still run with the old version, whatever version you specified here, so you'll still be able to work on newer versions of CMake. Or if the person that's compiling has a newer version of CMake than the one that you wrote it for. This needs to be the very first thing that you have on a file. The next thing is project, and then you say project, name of your project. You can also specify some options. One of these is languages, and then you say what languages do you support. So C, CUDA, Java, whatever it is that you support. C++ inside CMake is called CXX. So if you ever see CXX and you're wondering what that's for, it's C++. And there's also another property that we can set on our project, which is the version. So if you're actually making some protection code, you might want to specify a version. This is my version 3.5.9, right? After you say your project, you can say version and then list that number. It can just be one number like 3, or 2 numbers, just the major and the minor, or you can go all the way out to 4. The general convention is that when you make changes to the major release, like when you go from version 2 to version 3, is that version 2 stuff is not compatible with version 3 stuff anymore. If you change the minor portion generally in release, that means you've added some features, right? But you didn't break anything that was already there. So if you move from version 3.5 to 3.6, all the old stuff works, but there might be some cool new things along there as well. The patch is normally for like fixing bugs, but you're not really adding anything. Or you might do some optimizations to speed things up. Generally, that wouldn't be a new minor increase. It'd be like a patch increase. And tweak, I've almost never seen anybody use tweak. Generally, it's always got 3 numbers, but if you had something even like smaller than the patch, you'd put it in the tweak. That's just generally convention that users know how to use your project. But as you've seen with us, we don't have any versions in our projects, and that's okay, because I don't think we're planning on releasing this for everybody in the world to use. We can find a list of languages supported by CMake over here, which actually defined it on Stack Overflow because it wasn't on the documentation. So ASM is assembly, ASM ATT is AT&T assembly. I'm not sure what MASM is. NASM is another dialect of Intel assembly. You have C, C#, CUDA, CXX, again C++, Fortran, Java, apparently RC is something specific to Windows, and Swift. So those are the languages that you can support like out of the box with CMake. The next command that we saw back here was the set. Set is the command that's used to create and initialize variables. So here I'm trying to set the CMake standard to be 11. So I want to compile for the 2011 standard. And these, there are a lot of built-in CMake variables. And they can contain a lot of useful information. And they also can control a lot of behavior of how things work as well. So I'm just creating and specifying that we want to do for the 2011 standard. For example, if you go here, here's a list of all of the CMake built-in variables. I've not looked at most of these. Yeah, I know, right? That's why like CMake at first can seem like really like overwhelming, because there are so many of these built-in variables, and like the documentation for like how they work is not always that well defined. So, like you say click on CMake, name of archiving tool for static libraries. That specifies the name of the program that creates archive or static libraries. Do you know that much more after reading this? No, me either. The archiver is the tool that's used, like it says, to create static libraries. So it might be something like GCC might use some internal tool. I don't know what it does. That archiver for creating static libraries. But if you needed to know its name, that's where it's at. They have a lot of other things. Like this thing might make sense, like the CMakeCache major version. This stores the major version of CMake used to write a CMakeCache file. So you know what the version of the program is that writes CMake's cache files. It's a major version, if you needed that. So yeah, there's a lot of stuff there. And of course, you can create your own variables as well, which we'll talk a little bit about that in a second. So then the final command is the add executable command. So you say add executable, the name of your executable, and then you list your sources out. There's also another option that you can add called exclude from all if you don't want this thing to be built automatically with other executables. Your project can have more than one executable, and that's completely fine, right? You might want to build multiple different executables at the end of the day. If you don't want it to be built automatically, though, you would use the exclude from all. List out your sources. It will then attempt to create that executable from those sources, unsurprisingly. So I don't know if any of you guys have ever had that error where you're inside like CLine and it keeps telling you like this file is not a part of this project. Anybody had that? Couple. It just means that the file wasn't listed in the CMakeLists.txt after the add executable command. So if you wanted to fix that, it's like, oh, bob.cpp is not a part of this project. Go into the CMakeList.txt and go into the add executable command, and then go add bob.cpp, and then we'll get rid of their error. Because if we didn't know it was a part of the executable, we wouldn't know to compile it. That's how you fix that part. Any questions so far? That's more or less the basics of what you need to know how to use CMake for simple projects. You don't need to know any more than that. I don't know much more than that. But there are also some other things that are a little bit nifty, and we'll talk about them in a second, and also over next week as well. So if you want to run CMake on the command line, it's generally recommended that you do an out-of-source build, which means you don't build in the same directory that all your source files are. So you create a new directory. A lot of times you call it build, cd into that directory, and then you would do cmake ... because the CMakeList.file is one level above you, and it will go and configure and generate all the files. Then once everything is complete, you would run whatever your native build command is to do the compilation. So for us, that's just make. So you run make, so you run the make file, and it will compile everything together. You want to do the out-of-source build to keep things tidy because you don't want all the files that are generated by CMake to be thrown probably into your source directory as well. It's really annoying to deal with, and might also cause some conflicts if things happen to be in the same way. CMake does do this out-of-source build directory by doing the CMake build debug. So everything that CMake makes here inside CLine is being placed here inside the CMake build debug directory. So it's nice not to have to look at all this stuff in here. So CMake will store the results of this last run in a file called CMakeCache.txt. If you've ever noticed, like when you first start a project, it takes a really long time to load up, but every time after that, it's pretty quick. This is because really the first time CMake is run, it's actually doing all the work of locating where the compilers are at and where things are at in the file system and double checking things. And it saves all those results into the cache file. So when it goes to be run again, it just looks inside the cache file for the old values, assuming nothing's changed. If things have been changed, it'll go update those as well. You can see what's inside this file because it's just a plain .txt file, and you can open it up and even edit things as well. So CMakeCache.txt. So you can see here are all these variables, like the CMake CXX flags debug string is equal to -g. If you want to turn debugging on, that's what you would do. But there's a ton of stuff in here as well. And if you wanted to, you could actually go in and change these things by setting them to be something else. But that's probably not a good way of doing things. If you want to set the variables when you're running it, what you do is you do -d variable name. Optionally, you can special a type. You don't have to do the type here, equals some value. And you can do this multiple times for every variable that you want to override. For example, if you want to change the type of the build that's done for single configuration builds, CMake -d CMake _build type, it's a string equals debug. And then ... to do the one level above you. That's where the CMake list is at. If you wanted to do release, you would change the value to be release. There's also rel with debug, which is release with debug, which will try to turn on all the optimizations and whatnot, but also still keep the debug information in there to help you find errors. If you do debug, it turns off all the optimizations and does the least amount of code change that it can, the underlying executable. So it's really easy to map your high-level lines down to the low-level language to be able to find the bugs. But normally when you release, you want the optimizations on, you want the speed. So you would just say, I want my build type to be release. Then maybe in your release with some of the optimizations turned on, it now triggers some bugs that you weren't able to find before because of how things have been modified. So you do release with debug, help you debug those. If you are specifying the type, it can be one of bool, string, path, file path, or internal. A string is obvious, it's a string. Path is the path to a directory, whereas file path is a path to a file. Internal is another name for a string, but for GUIs that are used by CMake, it won't display that as an option to the user. And then bool can be on or off, true or false, 1 or 0. Makes sense, I hope. Any questions so far? So if you want to create your own variables, it's set variable name. Then you can list multiple values, value 1, value 2, value 3. There aren't any types in CMake. It does strings for everything. And if you do value 1, value 2, value 3, it's actually going to turn it into a list. And lists in CMake are just strings that are separated by semicolons. So it keeps things as simple as it possibly can. If you want to access the value of a variable, you enclose it inside curly brackets and put a dollar sign in front. The $ myvar will get you the value of myvar. $ CMake build type gets you the value of the build type. Then you can set some variable to be some other variable. If you want to delete a variable and remove it from existence, it's unset. Any questions? Yeah. You probably won't. Like an example of using set that you might want to do, but don't have to, is if we go over here into our CMakeLists.txt, what we might do is we might want to do something like set sources to be main.cpp, brother.cpp, brother.h, sister.cpp, sister.h. And we're collecting all of our sources together, and now over here, I could do $ curly bracket source. And it's not going to do anything different. And it'll still like compile and everything just like it did before. Right? If you want to, I believe the variable names are case insensitive. We'll see if that's the case. Oh. Nope. Not case insensitive. So you can collect them together. Like the most advanced commands you're probably going to have to use are like set if you want to set some variables, find for finding things like end curses. Some of the target commands for turning on some of the options like the wall and the arrow that you've already seen. But CMake allows you to do like a lot more complicated things. Like you could like find Git, bring in Git, have Git download some package, compile that package, and then link it into your source code if you wanted to. Like link it into your project. It's doable, and you can do a lot of things. There's loops in it, there's functions in it. There's a lot of more stuff that I don't know how to use in it, especially like the built-in like commands or like the packages that come with CMake. They're really useful for doing a lot of things, but I just have never had need of them because my programs have been so simple. And our programs in this class are going to be simple, so you won't be moving beyond anything like more or less what your CMake list files have been so far. Anything else? Sometimes the variables value that you might want to save, you might want to put it in the cache, because these normal variables, they only last for while CMake is running, but you might want something to persist after, perhaps be used in the build. So if you want to set a value in the cache, it's set the variable name to its value. Then you say cache to say it goes into the cache. And then the type of the variable, again, string, bool, file path, path, or internal. And then a doc string, which is just some information about the variable, what it's used for. And then optionally, you can add this extra parameter called force. So normally when you add a variable to the cache, it's only added if it doesn't already exist there already. Sometimes you might really want to make sure that it gets to be set whatever you want. So you force it to be the value. And that will make it be set there even if it's already there. If you want to remove a variable from the cache, it's unset variable name in the cache. And then I didn't have time to finish the rest of the slides. So there were questions on pointers. Yeah. Yes, for the unique pointers. Smart pointers, right? The unique pointers and shared pointers all have a reset. And your question about them was? There's for the smart pointers, there's unique, there's shared, and there's weak. No, there is a reset for unique. When you reset a unique pointer, it will delete whatever it points to, because it's the only one that has ownership over the object. Are there other questions about pointers? Yeah. So if you reset a shared pointer, that if you give it no arguments, it means you no longer have ownership over that object, and you now point to null. If you reset and pass in a pointer to the thing, something else, right? You will remove yourself from owning that original object and now try to take joint ownership over the new thing. Anything else? Okay, I will see you guys on class on Wednesday, and hopefully I'll